In class, the very first exercise is to measure the reflection coefficient phase off of this cable. So this goes beyond the calibration. It's calibrated. I will connect this cable to port 1, and now the microwave goes out of port 1 all the way down to the end of the cable, reflects off the cable and comes back into port 1. And there's a little bit of loss on the cable, which you can see by scrolling the wheel. That little marker 1 is telling me the white number is telling me the frequency marker 1 is at, and atop the white tells me how much loss. So it gets worse with frequency. So at 900 megahertz, it's up to a half a dB of loss. Down here at low frequencies, it's 0.01, basically no loss. So that's the first measurement because you're reflecting off of an open circuit. Now, if I want to display the phase, I can go back and display trace. We can make the second trace a different mathematical calculation of the same data. So it's the blue trace, and now we want to tell it the format for the blue trace will make it phase. So now you can see the phase is evolving with frequency, and we can find the phase at 500 megahertz by moving this marker. So at 0 frequency, there's no phase shift. And as we go up and up in frequency, the wave goes down the coax, off the open circuit and back in. So it goes a length, it propagates the length 2L of the coax. So it picks up a phase of 2 times the wave vector beta or k times L. And beta, the wave vector, is 2 pi over lambda. So it picks up a phase that's proportional to the frequency. So as we go up in frequency, the phase gets more and more and more. And you can see here at 100 and some megahertz, the phase is minus 96 degrees. We go up to 180 megahertz, the phase is minus 140 degrees. When you get to minus 180, it flips because everything is modulo 2 pi, and it goes to plus 180 and it comes down. So we can keep going up to 500 megahertz is the extra credit problem. So there's the phase shift at 500 megahertz. It's minus 15 degrees. So that's how you measure the phase shift.